Okay, so we are talking about survival analysis, and I'm gonna give you an introduction. It's not gonna be statistically and mathematically thorough, but just more of a pragmatic way of doing some hypothesis testing with survival data. So the first thing, as you know, survival data is kind of unique in the sense that you don't have a unique outcome column. You have two columns that tells you the day and whether the event is observed. In this case, I just pulled a data set that I have where there's a time and then whether the patient fortunately died or not. You can use other events as outcomes. You can use time to retreatment, you can use hospitalization, you can use time to cognitive impairment, whatever you want. It's just this applies to any cases where you have a time and an event, yes or no. The reason why historically it was thought this way is that you can still use information for cases that are censored. That is, censoring is the word that we use for when we know that the patient was alive at, in this case, 1261 days, but we don't know what happened after. If we were to only use the patient that actually experienced the event, we would have to reduce the sample size and lose all of the information from patients who survived, and then we're lost to follow up at some point. So this is the concept of why survival analysis was invented to begin with. So survival analysis is a statistical method that handles censored data, essentially. This is the easier way to put it. There are two major flavors of survival analysis. It can get way more complicated than that, but this is a paper that I did that I pulled just because it's a good example. One thing that you will see a lot of times is log rank, where you have two curves for two groups, and the log rank tells you a p-value and a hazard ratio comparing the two groups and the two subgroups of patients, let's just say. Forget about what adjusted p-value is in this case. Let's not get there. But let's just say you have a p-value and a hazard ratio. The hazard ratio tells you what is the ratio of hazards between the two groups. So in this case, 7.3 means that the bad group has 7.3 increased sevenfold, 7.3-fold higher hazard of experiencing the adverse event compared to the other group. Okay? And the p-value tells you what the confidence that we have that there is a significant difference. The other flavor is the Cox analysis, and we're going to talk about that in a second. But so just to understand, when you say log rank, you also have to think like it's easily visualizable with two curves usually. Cox methods typically don't have curves that you visualize. So this is a table where I also did Cox. And in that case, so this difference was between volumes of the tumor. The volume of the tumor was also analyzed with Cox. Let's see why in a second. But it also gives you a p-value and it also gives you an hazard ratio. It doesn't give you curves. We're gonna see that why in a second. Um, I mean, you can calculate curves, but it's very convoluted. So let's just say typically Cox results are presented in a table rather than in a curve graph. So this is just as a very basic introduction. One thing that we have to understand is one thing is the plotting of the curves, the Kaplan-Meier curves, where we visualize the data over time. And another thing is the hypothesis testing of deciding whether or not a certain variable has an effect on the outcome. These are two different things. Of course, they touch each other and they interact with each other, but we have to have them separate in our brains. So first of all, let's get a little more familiar with the curves. I made up some data. So as with Prism, you can use a survival table to visualize the Kaplan-Meier curves. And just for a first showcase of the curves, I'm making up cases where all the patients experienced the adverse event. So this is why I called it mock data, no censoring. There's no censoring. All of the patients have an event, and if you look at the curve, you will see that every time you start from a certain probability of survival of 100%, and every time you see that part of your cohort experiences the adverse effect, the event, let's just say, the curve drops of a certain percentage that is representative of what percentage that single individual that experienced the event, what percentage of your cohort that was. As you can see, very important thing to understand, if we zoom in, the step of the gap of the I want to say the how tall the step is, it's gonna be maintained over the curve because each patient represents the same amount of percentage of the whole cohort. This is only true because there is no censoring. What happens if we have dramatic censoring? So in this cohort, I just modified this fake data to say, okay, what about almost everybody experienced censoring and we only have 2 events? Let's see how this modifies the curve. And this is an extreme case, but it helps us understand what is the difference, right? So as we saw before, the first step is just as tall as in the other case because one patient is still whatever 12% of the cohort, whatever that is. But then here we have censored events that are typically showed as sticks on the curve, censoring, 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 censoring. And by the end of this time interval, one single patient represents 100% of the leftover cohort. So when that other single patient experiences the event, you have one step that is the full amount. So this helps us understand how the curve is constructed and how to interpret it, because each single event will have a bigger impact on how the curve bends over time, depending on the censoring amount. Okay, so as we saw before, if the censoring is kept to 0, each patient has the same impact. But if as time proceeds, the more censoring, the more weight to each patient for the final tail of the curve. Okay. So what happens if you have partial censoring, which is a more typical thing, right? You have a bunch of patients, they have the event, and some other patients don't experience the event. This is more of a typical Kaplan-Meier curve that you would see. Again, it's very few patients, it's just fake data set, but you will see how gradually towards the tail, each patient contributes more to the curve being bent downwards, whereas one single patient event will have a smaller curve drop at the beginning as and more censoring, more contribute of the same patient. Okay, just to get an overall visualization of the Kaplan-Meier curve. As we are seeing the Kaplan-Meier curve, you can use it for a single arm. So you have only one arm of patients. You can also use it to describe what the survival curve is. And this is where you typically get those metrics like what is the median survival? You have to see where this curve hits 50%, right? Or what is the survival at 200 days? You have to see what is this curve Y value when X is 200. So these are the metrics. The metrics like PFS at median PFS or PFS at 1 year and stuff like that are all extracted from these curves. Okay. And as I was mentioning, the curve per se is not necessarily linked to a hypothesis testing. Like right here, I'm just constructing a curve from the cohort data that we have. I'm not even accounting for any variables. I'm not accounting for age or for anything like that. I'm just showing what the survival of the cohort is. Of course, it is tightly linked to showing the log rank differences, but we're going to get into that in a second, and it's not necessarily linked to that every time. Okay, so this is as far as understanding what the plot is versus the hypothesis testing. And we show that hypothesis testing has two different families, which are the log rank and the Cox. We want to show how to do a log rank to begin with. So this is a good example that we said, like we divided the group into cohorts by any possible discriminant that we are interested in. So in this case, it was whether the tumor was bigger or smaller than a certain amount. It could be I don't know, like blue eyes versus dark eyes, whatever we want that we can use to separate groups into categories. Okay, so let's just use this data set to make an example. So for instance, in this case, we have age, volume, whether there was a certain treatment, MGMT status, and whatnot. So a good example, for instance, would be to use a variable that is already categorical. Like that's the simplest way to do it. We're gonna get into other differences in a second. So a good way to do this would be, let's just pick a handful of these patients, maybe not all of them for now, but a good way would be, I'm just gonna pick the first 30 something just for the sake of it, but or whatever, 50 patients, okay? So when you do these things, you will work with a lot of different Excel sheets because you want to copy paste stuff a bunch of times. So a good way to do it is to use the filter, and then you can filter just one category, right? So you have everybody 0, 0, 0, 0 and their survival data. I'm opening Prism, just the same file that I had before. You do new data table, you say you want to do survival analysis. Here we go. And I'm going to call it MGMT survival 50 patients, just to remember that it's just a subgroup. I'm gonna paste it here. So 0 is the category. You don't need it. It's just there's a reminder for myself. And then there is the outcome data that is days. It's just beta row and then event, right? Now, what are we missing? We're missing the cases that have MGMT1, so the methylation status, but it doesn't really matter for this exercise what that means. These are the other cases. And you want to build it as you go to the top. You can even leave a split, it doesn't matter, like for clarity maybe. But the important thing is that, yeah, let me correct myself. The way Prism works is that it's expecting two different rows or many different rows depending on the amount of patients. So this would be unmethylated, which is the zeros. And then if you want the methylated cases, which are the ones, you have to move them in their appropriate column. Does it make sense? This will do two things. First, it will automatically construct survival curves. These are the numbers related to the survival curves and the plot of the survival curves, okay? And it will also calculate the curve comparison with the log rank, okay? So you see log rank p-value, very significant, and the hazard ratio of the log rank is 3. Again, it's 3 of group A respect to group B, or 0.3 group B respect to point A. Of course, they're specular, of course. So this means that one group has threefold more risk of experiencing the event compared to the other. Okay, everything clear, I think? Okay, so this is a first example with dichotomic variables. But as we said, we don't only have dichotomic variables as MGMT. We can have also continuous variables like age. When you have age, there's two, well, so first, well, no, let's just continue. When you have age, if you want to do a log rank, you have to come up with a binarization way, with a binarization strategy. So I'm just gonna, again, copy some of the patients to another sheet, and I truthfully just want to look at age for now. So, I forget what is the if function. Forget. Well, I forget. You could write an if function. I forget the Excel syntax for it. You can write an if function to say what if is it below or above a certain category. I think it's worth spending 1 minute to do it properly. I'm just gonna Google what the syntax is. If syntax Excel. It's equals if then this above, let's say 50, let's just say 60. I'm just making up a cutoff right now. Then we're gonna talk about how to decide cutoffs when we have to do this. And then so if it's above 1, if it's below 0, okay? And then you can just expand this, right? So this is a I just created a binary variable that tells us whether the patient is above or under 60 years of age. I'm just going to call it age 60. And just like before, we can do the same thing, right? So I'm just going to duplicate this. Yeah, it's probably 60 patients, whatever that is. Age 60, I'm going to call it so that I remember what it is. And then it's going to be age above age 60 plus, age 60 minus, whatever you want to say. Clear this, I'm going to clear this, and then we do essentially the same thing that we did before, where you can apply a filter. So in this case, our patients less than 60 years of age, just like before. And now we have to compile cases, include cases that are above. Okay. Of course, if you want, you can code this for Python to do it automatically. You don't have to do copy pasting, but I don't know, like especially for the first times, like Prism is pretty user friendly, depending on how many analyses you want to run. But if you have a lot of cases and different variants, maybe you want to code it. Otherwise, it doesn't matter. So again, it created Kaplan-Meier curves for the two groups. Of course, well, I mean, you would probably have to. It's indistinguishable otherwise. You probably want to change the color. So yeah. So whatever. I maybe flipped them because it looks like the older ones are going better than the other ones. Probably I was doing things fast and I flipped the categories. Anyways, this is the idea of dividing two groups to have log rank groups to compare. Very quickly, I'm going to say if you happen to have more groups, like it could be age. Now I'm just gonna change this data arbitrarily just to show a point. If you had 30 to 60, and then 60, 70, and then 70 plus, so you would have 3 categories, and you have another group here. So this would be group 2, right? Where you have, I'm just gonna copy paste the data. Just, of course, it's fake data. I'm just trying to show a certain thing, and then you can have, just gonna make up some numbers. So now you would have 3 curves. Well, probably having true data would be more helpful than what it is, than what I'm doing. And there is a difference in how you analyze this data set. You still wanted to do survival curves, analyze table again, and death event. Okay, you have a bunch of things to specify. The important thing in this case is to look at this aspect: log rank test for trend. For trend, you use it if you have more. So first of all, it will not show up if you only have 2 groups. It only shows up if you have 3 plus groups, and you should only use it if you have 3 plus groups that are ordered, like you have that where group 1, group 2, and group 3 are in a certain type of order, because it's gonna test whether there is an incremental effect on prognosis of these 2 categories. For instance, these 3 age groups that are incremental, or 3 different risk factors groups, like 0 risk factors, 1 risk factors, 2 risk factors. This is the exact thing that I did actually here. Probably should have shown this before, where you have no risk factors, 1 risk factor, 2 risk factors, and you want to show log rank for trend, because it captures whether there is an incremental effect in the groups. Okay, so this is an overview of log rank. What are the advantages? The assumptions are, well, there's no assumptions. I mean, there are assumptions, but let's not go there. Let's just say you want to use it when you have categorical variables, or you can use it when you have a good way of dichotomizing or grouping continuous variables into categorical variables. How do you, well, let's just say right now, how do you decide, let's say you have age, and you want to show a log rank, how do you decide where to use the cutoff? You have some different options. One option is if you have a strong biological reason to group things a certain way. For instance, a certain thing happens at a certain cutoff of a certain variable and it's being reported biologically, and you say, okay, since biologically this means that, I will use this cutoff. That's an idea. Another idea is where there is prior literature, and this is, by the way, to some extent, well, hold on. Biological reason, a good example is your article when you're doing differences of growth rates. Because 0 is a cutoff that means something biologically, because a cutoff difference above 0 means the tumor is growing more than it was before, and below 0 means it's growing less than it was growing before. So when you can tie back a biological reason to a certain cutoff, you're allowed to justify it like that and explore that analysis. Another way is if you have prior literature, you have a couple of prior papers that show that in this specific disease, age 70 really dictates a major change in prognosis, then I'm going to use age 70 and say, look, like it's been validated before, I'm just using the same. What if you don't have those things, or you don't want to use them, but for a number of reasons? There's another strategy that we use a lot, and I'm pulling one of prior papers by Ben because it shows it very well. You can optimize the cutoff. So what they did here is they ran log rank while they were testing different cutoffs of ADCL in this case, so just an ADC marker. So they started 0.8 and they tried to separate the curves. They tried 0.81, they tried 0.82, and they plotted what is the p-value and the hazard ratio across these different cutoffs, potential cutoffs. And they say, okay, there is an effect and there is a maximal effect at a certain cutoff and around it. So these are the optimized, let's call it, cutoffs to separate the curves the best it is possible. Okay? Just to give and we have code to do this if you want to do it this way. Okay, so I think this covers the majority of the log rank aspects. Let's talk about Cox models. Oh, well, one thing that I didn't mention is the big advantage of the log rank is that by categorizing and having a p-value associated with two groups, you can very easily show a plot, like here, right? You show a plot, these are the two groups, these are the observed survival curves of these two groups, and you show the difference according to these two groups. So it's very much easier to communicate. And the interpretation is very straightforward when it says 7.3 means 7.3 of one group compared to the other one. Whereas when you have a Cox model, we're going to get to that in a second, the interpretation is a bit different. We're going to see it is a bit different, and we're going to see that. But most of all, I don't have a curve. I could calculate it. It's very complex, but I don't have an immediate curve to show. I mean, if I calculate it, it would be a modeled curve. There's a couple of things to say about it, but you don't have a clear, evident, observed curves for the two groups that we're talking about. So this is definitely an advantage of log rank. So let's talk quickly about the Cox models. Why would I decide to use a Cox model? So first of all, I can use a continuous variable without dichotomizing it, which is obviously an advantage. The assumption is that this continuous variable, so for instance, age, I can use it without saying below or above 60. I can say, I can input in the model 51, 52, 53, and so on. The assumptions behind it is that the model converges in a way that it assumes that there is an incremental effect that is proportional. It's called Cox proportional hazard model. So there is a proportional effect of the continuous variable on the outcome. Okay? So typically, if you use a Cox model, it's not necessary, but you typically use a continuous variable as a continuous variable without dichotomizing. You can also dichotomize it, but that's a different story. So let's make an example where we have, for instance, all of these patients, just copy pasting everything, and I'm removing the other ones just for a second. So we just have age and the outcome. Prism does, the latest versions of Prism can do Cox models, or you can code it with Python or whatever you use, MATLAB. Another way to do it quickly is that there is a online calculator that we sometimes use to get a sense of the effect that we're looking at. So this is the calculator. I can link it to you. Sometimes we do exploratory analysis with this. So you can just arrange the data as such, variable and outcome in time and event, and then you can copy it just like this, okay? It wants to know the number of predictors. In this case, we haven't gone into multivariate Cox yet. It's univariate Cox, so it's just one variable. So one is good. And it wants to know the number of data points. So in this case, it is 592 patients, 592. 592. And you can run it, and it's going to converge.
Oh, I think it's blocks above.
Oh, sorry. Yeah, perfect. My bad. And then one. Thank you. That was confused. Okay. So, and there is an output. The output is variable one, because we only have one variable, right? So if it was multivariate, it would have multiple, but this is the beta coefficient. No, sorry. Yeah, this is the beta coefficient. This is the standard error of the coefficient. Okay, let's skip that for a second. What essentially we want to look at real quick is the p-value, which is 0.0000. Of course, p-value 0 doesn't exist. It's just going to be 0.00001 or something. And it cropped the digits at some point and rounded to 0. But you can say less than 0.0001 and you call it a day. So the hazard ratio is 1.017, whatever, let's just say 1.02. And the confidence intervals are, of course, all around this number, and both are above 1.0, which tells us that the p-value is significant. I mean, it would usually, when the p-value is not significant, the confidence interval crosses 1. When the hazard ratio is perfectly 1, there is no difference in the variable has no impact on the outcome. So 1.017, 1.02, let's just say, it looks like a very small hazard ratio, but you have to remember that this is a proportional model and it has to be interpreted as every unit of the variable is gonna have a 1.02 additional hazard, let's just say. So it's zero, actually, a 0.2 additional hazard in the risk of in the hazard of the event, okay? Which means it's going to be cumulative after 2, 3, 4, 5 years. So this is the hazard ratio for each additional year of age in this case. So this is how you interpret this. And importantly, you want to scale your variable appropriately before you input in the model. For instance, if we used tumor volumes in cubic millimeters and we just threw it in here, we would have a hazard ratio that is 1.0000000, and we probably even wouldn't be able to see the significant digit because it just would round up to 1.0. And even if we do, it's very hard to interpret, right? So you want to scale it in a way, for instance, in CC is already better, where you have it has a ratio large enough, or like with fewer decimals that you can read better, right? So this is 1.02, it means 2%, essentially. It means 2% more hazard, like increased hazard for each year of age. This is the way you interpret it. Okay, so this is pretty straightforward. You could even binarize it again to 0.50 and run it with a binarized variable 0.1, but let's not do that because, I mean, at that point, you probably use a log rank unless, I mean, there are reasons to use a Cox we're gonna get into that in a second. The last thing that I want to mention is multivariable Cox. What is multivariable Cox? Is another one of the advantages of the Cox model. Log rank cannot adjust for any other variables. Why? Because you're just separating a certain way, right? You can combine different things. For instance, here I had a volume group, two volume groups and two sphericity groups, and I'm grouping them saying small volume high sphericity or high volume high sphericity. You can combine things like that, but you cannot fit a model that accounts for multiple variables. Cox models can do that. So for instance, this whole data set where we have age, baseline volume, treatment, GMT status, and the outcomes, we can throw all of these into a Cox model. And I'm going to do that in a second. So you can copy everything. Let's get back to the calculator. Let's wipe it. So this is the full data set that we have. Still 592 patients, but now we have 1, 2, 3, 4 predictors. Okay. You solve and it converges. It converges. So variable 1 was age, and we still have a very similar. See, it was 1.017, and now it's 1.02 because now it's adjusting for all the other variables, right? So it converges a little bit different. Now, the second variable, it's also significant. It's the baseline volume. And here is the problem that I was mentioning before. The volume here, this is a raw data set that I didn't use at the end, but you see the volume is in cubic millimeters, and we encountered the exact problem that I was mentioning before. The hazard ratio is 1.0000, not because there's no effect. Indeed, the p-value is very, very low, but simply there's the hazard ratio was rounded to 1.0000 because it's probably 1.000005 or whatever, right? So this is a good reason why, I mean, if we rescale this, I'm not gonna do it now, but if you rescale it to CC, so instead of 39,000, you have 39, then the hazard ratio starts to be more readable because it's not converging to the effect of a single cubic millimeter, an increased volume, but it converges to the effect of a full CC of volume. You can scale it however you want. You can even scale it to, you can scale the age to decades, right? Instead of 37 years, you can scale it to 3.7, and then the hazard ratio will be read as what's the increased risk, increased hazard linked to a full decade, to being older a full decade, right? So you can scale variable as you want, and then you can read the hazard ratio accordingly. There's also a way to fix the hazard ratio on the back end to reflect the rescaling, but that's a bit more convoluted mathematically. So I would just suggest that you scale your variables the way that you want to begin with before running the model. And then again, you have variable 3, variable 4. Let's not get into all of them, but for each variable, you have a p-value and a hazard ratio with its confidence interval. So that tells you the reason we do multivariate Cox is that it tells you what is the effect of the age adjusted for other things, okay? And it tells you what are independent predictors when all of them are put in the same model. One thing to be mindful about is collinearity. When you input in the model things that are very highly related to each other, one is going to kill another one because the model is only going to show you independent predictors that are independent of each other. So if I put, let's just say, I put weight and height, they're probably very related, and maybe only one of them, if there is an effect, will emerge as a predictor. There's ways around it. Usually you would do two models, one with the other. You compare the performance of the models. There are ways around it. But just to know this. So back to the assumptions of the Cox model, it assumes that there is a proportionality to the continuous variable. It assumes when you use a multivariate model, well, of course, might be mindful of collinearity, as we just said. You can test collinearity. You can see if your variables correlate with each other or not before you do it, if that's a way to do it. Another thing to be mindful about is that this model, the way it is it expects the same effect in all subgroups. So for instance, if paradoxically, tumor volume matters in old people in a certain direction, but in the other direction in young people, it will not be able to disentangle this because this is a very hard example to understand. But let's just say you have let's say that one of the variables is a treatment regimen, treated with drug A versus drug B. And let's say that drug A does very well in young people and drug B does very well in old people. A model like this is not going to be able to disentangle that because it assumes the same effect of age on drug A and drug B, or the other way around. It's mathematically the same thing. It assumes the same effect of drug A, good effect, let's say, correcting for age, but it cannot tease out whether the effect is opposed into different age groups. So just to understand how the mathematics we're not looking at the equations because that would be overkill for this introductory thing, but just be mindful of these subtle aspects. The last thing I want to mention is you see, for instance, MGMT or the treatment arm are binary and I'm still inputting them in a Cox model. That's perfectly fine. Of course, if a variable is binary, the hazard ratio just tells you what the incremental hazard is when that variable is 1 compared to 0, end of it, because there's no 0, 1, 2, 3, 4. It's not a continuous variable. So just know what your data looks like when you're interpreting the final results. Yeah, that's it.
I just had one question, I
Yeah.
think. When you're reporting for the Cox model, will you normally, and you're looking at multiple possible predictive variables, will you report both univariate Cox analysis and multivariate for whatever you want to control for, or will you just report?
Yeah, that's a good question. So there's no clear there's multiple approaches are valid, right? So one way to do it is I think that this variable is important. So I'm showing univariate that it is important. And then I'm adjusting for other things that are already known to be important, like age is known to be important. So let's say my new variable, let's call it new variable. New variable, let's just call it something more sensible. Let's just say I have a MRI biomarker of whatever sort, and I'm saying, okay, this is prognostic, and people that have this phenotype on MRI are gonna do better, right? Let's say 1-0. Biomarker, yes or no. Radiologic sign, yes or no. And I want to say, okay, look, I do a log rank and I show two different curves. Great. And then I'm saying, okay, but is it still independent of age, or maybe it's just that I'm capturing that older patients have this biomarker, and then we're back to age, right? And then maybe I do a Cox when I'm saying this biomarker is still predictive when adjusting for age in a multivariate. So it has to do with your narrative. Other things that are done are a lot of times I'm testing 3 or 4 different univariate analysis, and then the ones that are predictive, I put all together in a multivariate model to see which one survives. This tells you some things that are important, but also has some blind spots. There's a couple of blind spots. One thing that I can think of on top of my head is maybe some variable is only significant after adjusting for other things, right?
I see. I see.
So you have to play around with things a little bit, but yeah, I think this is was kind of comprehensive on how to do things.
For sure. Thank you very much. I really appreciate it.
All right. Hold on. Before let me just no, I think it's fine. I think we covered everything. All right.